So now we've defined the Fourier transform, let's see how we go about computing one. The first function we'll look at is a Tophat function. So that is just a function that is zero everywhere except between some interval of width b, which I've placed symmetrically about 0 here. So the width of the function is b. We're going to write it using this notation here, a little Tophat symbol, x divided by b. So when b is 1, the width is 1. The Fourier transform then, that will be some function of k, is given by the Fourier transform of our Tophat function of width b, which we can write as an integral over the entire domain from negative to positive infinity, Tophat function times the kernel e to the negative I k x dx. Now we can simplify this integral a lot because this function here is 0 everywhere except the interval negative b to plus b. So we can change the limits of this integral to just being from negative to positive b on 2, and in that interval the height of the function is just 1, so there's a 1 here, multiplying our kernel e to the negative I k x dx. This is just the integral of an exponential, because negative I k is a constant, x is our variable, so the integral looks like this, which we can expand to give a sine function, the difference of these two exponentials here and the factor of I out the front give us a sine function. We can continue to rearrange this a little bit by multiplying top and bottom through by b and taking this factor of 2 to the bottom to write it as a sinc function, where sinc is defined as sine x divided by x, or sine k divided by k. So the Fourier transform of Tophat is a sinc function. If we plot it out, it looks like this. The height of the sinc function is b, where b is the width of this interval. So make the interval wider, the height increases. As we make b narrower, the height will decrease, and also the position of this first intercept increases. So as b gets smaller, this function here becomes wider and wider. And this is a common thread with Fourier transforms. We'll see this every time we do a Fourier transform of some function with it sort of peaks over some finite domain. The narrower the function in x, the wider the Fourier transform in k. Or if this were time, the narrower the function in time, the wider the Fourier transform in omega. And this is actually telling us something kind of physical. And that is, if you have a function that changes rapidly, goes up and then down rapidly, to capture that behavior, you need to have higher frequency components. You need to have a wider range of frequencies in your Fourier transform. So a function that is narrow, that ascends and descends quickly, becomes wider in Fourier space to give you these higher frequencies that model this behavior. So this is the Fourier transform of a Tophat. It's also interesting to compare this to the Fourier series, which is very closely related, as was said before. So with some function, I'm just going to define this as having a width 1. So in this case, b is 1 in our previous definition. The height is still 1, so the function is this. The Fourier transform, written using the notation now where we're summing from negative infinity to positive infinity over m, the Fourier series is written like this. So here are our coefficients here, and we can see these coefficients actually take the form of a sinc function. Here we've got sine m pi on L divided by m pi on L. So this is sinc m pi on L. So these are our coefficients of the cosine functions because it's an even function. What we're going to do now is allow L to increase. So L, remember, is the domain of which the Fourier series is periodic. So outside the edge of this domain here, this Tophat function would just repeat over and over again. But if we make L larger and larger, and as L tends towards infinity, we should recover something that looks like our Fourier transform. So here's an animation of this happening. Here is L equal to 2, and we can see our discrete points here. This is the frequency spectrum of our coefficients am, the coefficients in this Fourier series. And as we increase L, this is what happens. We have more and more points appearing in this frequency interval. The width of this function is not changing because we're not changing the width of our peak here, but the number of points increases. And as the interval L tends towards infinity, this would tend towards a continuous function. And that would be the Fourier transform.